Yeah, go ahead now. What were you saying?
No, no, I was just saying the section is very good, like it's like easier because you can test back with the original function.
Yeah, exactly. I mean, so, and that process that I showed you, I don't think you were here yet, but I showed the function and I showed the derivative and I showed the second derivative, and I'll do that again today. Uh, so I can see that it'll seem like I get my derivative correct. It's a nice way to put a little double check in. Did I get my derivative correct? Okay. And so I knew I was doing that in chapter 4, so I didn't really do it in chapter 3, but that's fine, right? Um, so here we go, second derivative test. So I want to talk about what this will give us, what this will tell us about the original function, and right, and what I have to conclude about. So first of all, this is a second derivative test for concavity. Uh, uh, Inflection points, and local mins or maxes. So it's a three-step conclusion. I first will give intervals of concavity, and of course, so concave down, right? A function like this is concave down. So like y equals minus x squared, it's concave down. To me, it looks like a frown, right? So when the second derivative is negative, I'm going to be concave down. So for example, y prime is what? Negative 2x. Y double prime is negative 2. So negative 2 is always negative, right? So my function is concave down always. Concave up would be like a smile, right? So y equals, doesn't matter, so just keep it simple, right? X to the fourth is a smile, right? This is a frown. This is concave up. Positive people smile, so when my second derivative is positive, right, I'm concave up. So y prime is what, 4x cubed. Y double prime is 12x squared. And of course, x squared is always positive, so 12x squared is always positive. So there's my concavity. Now look at both of those cases. Notice if I had a local maximum, it'd have to be on top of a hill and the function would have to be concave down there. So I can use my second derivative to show that I have a local max. And then of course, right, so if my second derivative is negative, I have possibly a local max if it exists, right? And if my second derivative is positive, I have possibly a local min. And the last is our inflection points. These will come from our critical values of the second derivative, right? So our inflection points, so for example, well, 1 over x, right? 1 over x is concave down on the first part and concave up on the second, right? So this, oh, I'm sorry. I don't want to use that, sorry. Let me use arctan. So you can see arctan is concave up on the first part, concave down on the second part. And at 0, 0, if you can imagine, I'm driving on that road. So I'm looking down on the paper as if I'm in a helicopter looking down on a road, right? I can't tell if the road's going up in the air, but I can tell which way the car is turning. So if you see at first I'm turning, so here's my car. I'm always, right? I'm always left to right. Actually, I should draw the car like it's like I'm on top, right? So there's my car, pretty primitive. So I'm looking at the top of the car, and I can see the person driving must be turning to the left originally, and then when they get to 0, 0, they start turning to the right, and that's an inflection point, right? And so it's where is it? It's where the second derivative changes signs, either positive to negative or negative to positive, and the function exists at that point, right? That's my inflection point. So where the concavity changes. And it could change without a point, like 1 over x changes without a point, right? 1 over x is concave down here and concave up there. So I still have a change in concavity, but the point where it changes doesn't exist in the original function, right? At 0, this function doesn't exist, right? All right, so there's my process of what do I get out of the second derivative, right? So you see it's a couple of extra things, and of course I have to find the first derivative, I have to find the criticals of the first derivative, I have to find the second derivative, I have to find the criticals of the second derivative, I have to do the sign table, I have to check the second derivative, I have to conclude, right? So the process is the same, let me write it anyway. So step by step here, right? So my screen is out completely. I cannot see you at all. So just if you want to ask a question, just say it to me, okay?
Well, take a second to try and get us back if you can. I don't know.
I can't.
Could be good.
It's dead. I ordered a new one, so I can't do anything about it.
The yellow and the green died now. So.
Everything's dead now. I can't. Oh, there you are again. Yeah, I can only see yellows and blues. Okay, here's my step-by-step graph F. Right? Think about everything. Think about the domain. Think about the increasing, decreasing. Think about the local mins and maxes. Think about the concavity. Think about inflection points, right? When I say graph F, that's what I mean, right? Think about the whole process as you do it, right? Second step, find F prime and the critical values of F prime I'll call them C sub 1s. So anytime I say a C sub 1, I'm talking about a critical from the first derivative, right?
Yep.
Find F double prime and the C sub 2 values. So meaning the critical values of the second derivative, meaning where the second derivative is 0 or the second derivative is undefined, meaning where the numerator of the second derivative is 0 or the denominator of the second derivative is 0, right? Label the sign table / number line with the C2 values, with the critical values of the second derivative, right? And pick test values with C1 values when possible. So by the way, like a question I always ask for extra credit on this next chapter would be, can a critical value of the first derivative be a critical value of the second derivative, right? Can a critical value of the first derivative be a critical value of the second derivative? Think about it. So in this case, we've picked out our C, right? We've drawn our number line with our C2 values, right? So like if I'm picturing it, I can see maybe my C sub 2, sub 1, C sub 2, sub 2, C sub 2, sub 3, right? So I got 3 critical values of the second derivative. And if I can, I want to put a C sub 1 value as my test value, right? So if possible, put your test value in as if it's a C1 value, right? These are my test values. And my test is called the second derivative test, so I'm going to be plugging those values into the second derivative to figure out the sign of the second derivative. Okay? Yes.
For if possible to put like critical, like when we put C1 in the sign table, we can only do that if it like exists, right?
Exactly. Okay. Yep. If there were no C1 values in my first derivative, then so like for example, arctan has no C1 values in its first derivative, right? If y equals arctan of x, and I can see the graph, you can see I have no local mins or maxes there. I have no place where it's undefined, right? And I know y prime is 1 over 1 plus x squared. That never equals 0, upstairs or downstairs, right? So no critical values of my second derivative there. Of my first derivative, sorry. Find the signs, SIGN, find the signs of f double prime, right? Conclude about concavity. Conclude about inflection points. Conclude about local mins or maxes. And that can all be in, one little paragraph. But we have to make sure we mention those things if they happen, right? You don't need to mention them if they don't happen, right? So for the arctan function, I'm not going to mention anything about a local min or max, right? If you look at my arctan function here, there's no local min or max, right? But there is an inflection point. There's a place where where I'm steering, my steering changes, right? Where my concavity changes. And there's certainly intervals of concavity, right? The first half is concave up, the second half is concave down, right? Nice. How we doing? I guess.
Yeah.
Oh, you're okay. We okay? Anybody not okay? Anybody need a moment or anything before we do a problem? I see a hand.
Yeah, give me a moment, please.
Yes. So remember in homework that I assigned, right? You've got in the book it says do increasing, decreasing, concavity, local mins and maxes, inflection points. But when I say to you only do the first derivative test on it, that means do my 8-step process for first derivative test. Don't follow the book's instruction there. On all of them, I want a graph, right? I want you to be able to show me that you're correct, okay? And that could include just the initial graph with the appropriate labels, and it could also include the graph of the function, the derivative, and or the second derivative, right? Because that's the one that's really going to give us a clue that we got our derivatives right. And our critical values. You can clearly see where the road would change when you're driving, right? You could feel it in the steering wheel, so you know you'd have to get the correct critical value there, right? All right. So Markins, yes, we're good.
Yes, I'm good. Thank you.
Thank you. Let's see how many people are here today. 3, 6, 9, 12, 18, 19. Missing.
What the fuck? How the fuck do you get 19? There's 17 participants.
Oh.
Oh, I'm sorry. I didn't even know I was unmuted. That was my fault.
Who is that? Delilah? Nice.
I'm sorry.
It's okay.
Human moment.
Bruh, I'm my fault.
I don't care. 3, 6, 9, 12, 15, 16. You're wrong too. You're fucking wrong. Sorry.
That's true.
Because I don't count myself. I'm looking for 20 students on my roster. Oh no, I don't have 20 anymore. I have 17.
You have 9.
No, I don't. I'm down to 17. So I'm missing one student.
So what, did we lose like a total of 5?
We lost 7.
Okay, yeah, plus the 2 that we lost earlier.
Yep.
But like recently.
Yep. And there's like I said last time, there's lots of reasons to drop a class. Okay. All right, let's do a problem. Let's do one of my favorite problems of all time. I think it was on your last test. Y equals e to the minus x squared over 2. I know this graph because I use it every semester. It's a bell curve, right? So first of all, we're looking at that graph. We see the domain is everything, right? We can see a local max on top of a hill. If I drive on that road, I can see myself turning my steering wheel twice, so I can see 2 inflection points. I can see concave up, and in the middle concave down, right? So I'm pretty much set for my second derivative test here. Everyone with me on that? Following that? Trying to think of who's missing. Okay, so first derivative, just simple chain rule, right? So y prime is negative 2x over 2 e to the minus x squared over 2. So negative x e to the minus x squared over 2. We okay there? It should be that quick. All your derivatives should be very quick, and especially in Calc 2. What we're going to start to learn is undoing a derivative. So we'll start with a derivative and try and get back to the function, and then how will you check those? You'll take the derivative of your answer. Go ahead, Jess.
Did you not chain rule the stuff in e to x?
I did it first. So the derivative of the inside is here.
Got it.
Right?
I see it now.
Yep. Good. Y double prime is going to come from a product rule. So I have a negative x, I have a negative 1, I have an e to the minus x squared over 2, and that of course is my first derivative, negative x e to the minus x squared over 2, and product rule. How are we doing there? And by the way, Delilah, there are 3 types of mathematicians. I don't know if you knew this, but 3 types of those who can count and those who can't. And I'm obviously one of the 3. So here I can factor out my original. Is everyone okay? Do we get this derivative? We get the second derivative? I kind of like, I want to draw these first. I want you to see this piece, but I really should get critical values, my C1 values and my C2 values, because that's the part of it that I want to see. But let me factor this factors nicely, right? I can take out an e to the minus x squared over 2, and I get an x squared minus 1. Oh, that's nice because I can see those critical values quickly, plus and minus 1. Right? I can see the critical value of the first derivative is 0. Right? So C1 values is x equals 0. C2 values x equals plus or minus 1. So I see my criticals of the first derivative and criticals of the second derivative. So I want to go to my Desmos now. Okay? I want to go to the Desmos now and then take a look at this little nice way of cheating. So f of x is e raised to the negative x squared over 2. There it is. Nice little bell curve. I want to graph my derivative, which was negative x. So y equals negative x times f of x. Right? I can cheat that a little bit. So there's my derivative. Notice that when the blue is increasing, so x equals 0 is my critical value, right? X equals 0. So I can see that purple line. So when the blue curve is increasing, you see my green derivative is above ground. It's positive. And once my blue curve starts decreasing, you can see the green curve, which is my first derivative, go underground, right? So this is a nice way to check that I possibly have this derivative correctly. Of course, it wouldn't change if I got it as negative 2. It still is looking like I have it correct, but hopefully the criticals will fix any kind of little error like that. You might not see that you have an error in your first derivative until you do your second derivative, right? Is this okay that I'm writing it this way? That I'm referring back to the e to the minus x squared like this? Because I'm a little lazy about it. Let me put in the second derivative. So I had f of x. I had that original e to the minus x squared over 2 times x squared minus 1. There's my second derivative. Okay, now look at the first part where it's concave up. Oh, where are my criticals? X equals plus or minus 1. X equals negative 1. And x equals positive 1. So you can see I'm putting those vertical lines in to show where things should be changing. So notice the first part of the blue curve, right?
Can you move your mouse just slightly?
Yeah. So notice the first part of the blue curve where it's concave up. My second derivative in green is positive above the x-axis. In between the criticals, the blue curve is concave down, and look at the second derivative. It's negative there. Negative people bring me down, right? Second derivative is negative. The original function is concave down. And then past this critical value of 1, I can see my blue curve again is concave up, right? You can see like the left hand of a smile, and you can see the second derivative is again above ground positive. So this is a nice way to double check that you've got things correct. Again, it is possible to plot a point on the TI-8384. It is possible to graph a vertical line on a TI-8384, but you got to look it up. I'm not spending time on that. So if you want that kind of little feature, you got to do a little work on your own there. Nice. Okay, let's finish our second derivative test. What do I need next? I've got my first derivative, got the criticals. Got the second derivative, got the criticals. I need to create my sine table number line, right? And so for my second derivative test, the only thing I'm testing is in between minus 1 and plus 1. So those are my C2 values, right? Those are my criticals of the second derivative. I want to put test values in. So less than negative 1, how about negative 2? Bigger than positive 1, how about positive 2? And what do you want to put in between? Well, I have a critical value of the first derivative of 0, so I want to test 0. So when possible, test the critical values of the first derivative as test values in the second derivative test. Right? So we want to find f double prime of -2, f double prime of 0, f double prime of +2. I don't have to put the numbers in. I can do it without bothering putting the numbers in. I can already tell that the middle piece of my curve is concave down, and so I must get negatives out of my second derivative. And the other two pieces are concave up, right? So I want to put positives there. And of course I could plug the values in my calculator. I could just look at the graph. That's what I did. I could do the values by hand, right? So for example, f double prime of 0 is e to the minus 0 squared over 2 times 0 squared minus 1. And that's obviously -1. So I get a negative. When I plug the value into the second derivative, I get a negative, and that's why that middle interval there is, right? It's got the second derivative sign, SIGN, on the line. I can.
And we're not keeping a dot on the number line for the critical value at the first.
Correct. Remember, so why did I want to find the critical values? Because it's going to tell me. So notice, first of all, that f double prime at 0 is -1, right? And that's so that's saying concave down, which means my 0 is most likely, in fact, is a local max.
Okay.
So it looks like. Go ahead.
We wouldn't want. Separately we would note that in the first derivative, not line.
Right.
We make.
Yes, but this is a special feature of the second derivative test. It would be awful for me to ask you to do both in one problem.
Okay.
It would take 5-6 pages. And then if I did, which I won't, you have an option of testing for local mins and maxes using the first derivative test or the second derivative test. And it's a lot quicker with the second derivative test. Right? With the first derivative test, the derivative has to change signs from positive to negative, and the point has to exist. In the second derivative test, I just have to show that the second derivative is concave down. So a lot quicker.
It just needs to be down.
Concave down is a frown, so the point would be at the top of the hill. Local max.
Oh, okay.
Yep. All right. It looks like I'm ready to conclude. I can do this. Yes, Markins.
Yeah, my question is, where did you get the 2 from?
The what one?
The 2 value, where did you get it from?
Oh, anything I want. So notice if I picked on my graph, if I had decided to test 2, right? So a comma 0 with a slider A. So I can test +2 and notice there that it's concave up, right? Or I could test +1.5 and notice there it's concave up. I could test anything. How do I know there's never going to change? Because if it did change, remember what a derivative is, it tells me how things change, I would get a critical value out of it. So if later on, like after 7, there was another change in the concavity, I would get another critical value, right? It doesn't matter where I test between -1 and 1, you can see I'm going to get a point on the curve where it's concave down. And maybe I should have done that as well, right? A comma f of a. Right, so no matter where I test here, you can see the point. So no matter what number I pick on the number line between -1 and 1, I'm always going to get a second derivative value that's negative. Right? So I can even do that, right? Y equals f of a times a squared minus 1. And so you can see there on my Desmos screen, I'm getting a negative value there for my second derivative, right?
Yes.
Yeah, and then if I go past 1, now I'm getting a positive value. So anywhere I check, right? So the solid blue dot is the x value I'm checking. The faded purple point is the value on the function. And the black horizontal line is giving me the height of the second derivative. So when that black line is above, I'm getting a positive. When the black line is below the x-axis, I'm getting a negative, right? So this is it's really, but all of that is stated here, right? All of that is stated here. So, but that's what I'm doing. I'm picking anything left of, right of, and in between the criticals.
Okay.
Yes.
Yeah.
So I got to do a conclusion. I know I have a local max. I know I have 2 inflection points. So I could do the work for those points in the conclusion, or I could do them ahead of time. I'm going to choose to do them ahead of time, right? So I know I have a local max, right, at what? 0, comma f of 0, which is 0, comma e to the minus 0 squared over 2, which is 1. So I'm just doing the legwork for my local max and my inflection points. I know I have inflection points. I know I have 2 of them. I can see them, right? So at plus or minus 1, f of plus or minus 1, which is plus or minus 1, comma e to the plus or negative plus or minus 1 squared over 2. Oh, look at that. Same as before. Lucky. Plus or minus 1, comma e to the minus 1/2, or plus or minus 1 at 1 over square root of e. And of course, before I go through my whole conclusion, I know I'm right already, right? But it's nice to kind of put those points in. So I had my local max at 0, 1. I have inflection points at negative 1, comma.
Wait, is you putting 2 equal signs denoting the one where it's positive and the one where it's negative? Because I think you wrote both of them as the negative, and you just changed the exponent by accident. One of those, the negatives cancel out.
No, the square is in charge. PEMDAS, parenthesis, exponent.
Yeah,
so I take care of the exponent
square.
first, yeah. So I've got my negative 1 over square root of e as my first inflection point, and I've got the positive 1, comma 1 over square root of e as my second inflection point. And so I can see all of that on the curve, right? Nice. Now the conclusion. Right, I've done all the work. I have the evidence. I know I'm right. I just want to make a nice conclusion here of what the second derivative test is telling me about the original function. F double prime of x is positive on minus infinity to negative 1 union 1 to infinity. So f is concave up on that same interval. F double prime of x is negative. The second derivative is negative. Remember, we're doing a second derivative test that tells about the function. F double prime of x is negative on minus 1 to 1. My intervals will always be open intervals. So f is concave down on minus 1 to 1. F double prime of x changes signs, and I don't care positive to negative or negative to positive. At that point, I have an inflection point. So F double prime of x changes signs at x equal plus or minus 1, and f of plus or minus 1 equals 1 over square root of e is a real number. So the points plus or minus 1 comma 1 over square root of e are inflection points. F prime of 0 is 0. F double prime of 0 is negative. And f of 0 is 1. So 0 comma 1 is a local max. I need the first derivative critical value, second derivative to be negative, and the point to exist, and then I know I have a local max. Done. Ugh, yuck. Whew, it took some energy for me to get myself to write that out and not just say, oh, I'll skip it, you do it. But I did it. I got it done.
That's 8 steps, and a couple of them just took 2 lines for you to write.
Yep.
The first one and I think the 5th one.
Mm-hmm.
Yeah.
I mean, we're looking at a good solid 2 pages of writing there, right?
Yeah. Especially if you write in big letters.
Yep. Or you use the sidewalk chalk, right? The big giant sidewalk chalk, and you're holding it like a knife.
Yeah.
Yeah.
That's how I used to hold a pencil.
Yep. Yeah, we're trying to be elegant. We're trying to be precise. We're trying to make things read well, right? We're going to make sure we're correct. And I think I had said this when you're handing in homework this time. Only send me the problems you did correctly. So if you can't do it, you better ask for help, right? But don't send me a problem that's not correct. Not only can you check it with the graph, you can check it in the back of the book, right? So.
Professor?
My dog's snoring. Yes.
Do we have to show you how we solve for the number line? Like the positive and the negatives?
No, because you're in Calc 1. I know you know how to plug a value into a function. And so that's why I'm saying we can cheat. Why bother doing that? I mean, I did it here, but why bother, right? This is like 8th grade work where you're plugging a value into something, right? So no, you don't have to. And that's why I keep saying I'm teaching you how to know you're right? I can just look at that graph there and see concave up, that's got to be positive on my number line, on my sign table. Concave down, that's got to be negative. Down, people that are down are negative, right? And then concave up again, I know it's got to be positive. So you can cheat that for sure. Sometimes it's hard to see it. Like if it's really close to a flat line, it's got a slight curve in it, then you might need to plug it in. But again, I don't need you to show me that you can plug in a number, right?
And the critical values, do we have to solve for that?
Yes, you need to solve for them, but like look at how quick it was for me and for you once I saw that second derivative, right? Once I saw that first derivative, do I have to set each factor equal to 0? Can't I just see that 0 makes it 0? Really, right? And this one, I can see plus or minus 1 makes it 0. So But that's why you're doing your derivative factored so that you can quickly see the zeros. That's why I've been stressing that all along, that we want to get a final derivative or second derivative completely factored so it's easy to find the zeros, the criticals.
Thank you.
Yes, you're welcome.
Could you please go back to the conclusion, please?
Yes, this horrible conclusion. Let me, and I don't mean to interrupt, but let me just stop my